Hello students, welcome to lecture 15 of this course. In the last two lectures, I have discussed about how to calculate energy of different atomic orbitals, and I discussed about how does a spectra of hydrogen look like. We looked at the gross spectra of hydrogen atom, and then we also looked at the fine spectra of hydrogen atom, which is due to spin orbit coupling. Now, I will go to discuss atoms having more than one electron. For example, helium atom. So, helium atom consists of a nucleus and two electrons, and if I try to solve Schrodinger wave equation to get the energy of different energy levels associated with helium atom, we will not be able to get the analytic solution, and this is because of inter-electronic repulsion term. Inter-electronic repulsion term between two electrons is given by E square divided by 4 pi epsilon naught R12, where R12 is distance between two electrons. So, what generally we do is to use different methods to calculate the energy of different levels associated with helium atom. One of the most common method is approximate method. In this method, what we do is first we assume that electrons do not interact with one another, and then we can ignore this potential energy term. This potential energy term due to inter-electron repulsion. So, in this case, when we ignore the inter-electron repulsion, we can express Hamiltonian operator as a sum of Hamiltonian operator of two individual electrons. So, we can just write Hamiltonian is equal to Hamiltonian for 1 plus Hamiltonian of 2, and for 1 we can write the Hamiltonian as minus h cross square by 2 m e del 1 square minus z d square by 4 pi epsilon naught r 1, and similarly for second electron we can write the Hamiltonian, and now overall Hamiltonian operator is sum of Hamiltonian operator of two electrons. So, approximate wave function in this case will be product of two wave functions psi 1 and psi 2, and Schrodinger wave equation can be divided into two separate equations given by H 1 psi 1 is equal to E 1 psi 1 and H 2 psi 2 is equal to E 2 psi 2. In this case, then energy of the system will be the sum of energies of the two electrons. So, energy obtained using this equation plus energy obtained using this equation. So, E will be the sum of E 1 plus E 2. So, if we take the approximate wave function and obtain eigenfunction of H 1 operator plus H 2 operator, what we will get is 2 E 1 s. So, eigenvalue obtained will be equal to 2 multiplied by energy of 1 s orbital of Hg plus, okay, 1 s orbital of Hg plus. Remember here Z is equal to 2. So, it will be 8 times minus 13.6 electron volt. If you remember, when we calculated the energy of the different orbits of hydrogen atom, what we got is your minus 13.6 into Z square by N square electron volt. So, energy of nth orbital of hydrogen atom or hydrogen like atom will be given by this equation. So, if I calculate this for helium atom, Z will be equal to 2. So, what we will get is minus 13.6 into 4 divided by N square, and if I take n is equal to 1, then we will get this 8 multiplied by minus 13.6 electron volt. So, this is your IN value for helium atom, and this is equal to minus 108.8 electron volt. So, till now we have calculated energy ignoring the repulsion between two electrons. Now, we will calculate the repulsion energy of two electrons, and that can be given by this formula. So, this is your potential energy due to repulsion between two electrons. So, psi star into this multiplied by psi, and then dV1 and dV2. If I integrate this, what we are going to get is 34 electron volt. So, repulsion energy of two electrons can be calculated using this method. Now, we have already calculated energy which does not include the repulsion energy between two electrons, and now we have calculated repulsion energy between two electrons. So, what we are going to do is we are going to add it up to get the total energy, and when we add it up, what we will get is minus 74.8 electron volt, and this is quite close to exact value of energy, which is minus 79.0 electron volt. So, this is the first method to calculate the approximate energy of helium atom. There are other methods reported. One of them is variation method. In the variation method, what we do is we take what is known as a wave function, which we think that this can be a suitable wave function, and then we try to get the energy. Here what was done is you consider effective nuclear charge Z dash less than Z as one electron is screen other, then the average energy will be given as this value. So, here I am not going to discuss in detail about variation theorem, since it involves higher hypothesis of quantum physics, and if you want you can go to NPTEL lectures on quantum and look how to calculate E dash, but here we start with a wave function which is known as trial wave function, and then you try to calculate the energy. Here what we generally do is, in place of Z we take Z dash, and that will give you E dash, and Z dash basically replaces your Z, which is your nuclear charge, and this Z dash is called effective nuclear charge. When you do that and you solve the integral, what you will be able to get is this equation. So, E dash is equal to Z dash square minus 27 by 8 Z dash multiplied by E square by 4 pi epsilon naught A naught. Now, question is how to get this Z dash. So, you have to choose Z dash to give the lowest energy by minimizing E dash with respect to Z dash, and when we differentiate that, the equation which I have given in the previous slide, you will get d E dash by d Z dash is equal to 2 Z dash minus 27 by 8 E square by 4 pi epsilon naught A naught. If you do that, you can get the value of Z dash. this put this equal to 0 and you can get Z dash minima, and that is equal to 27/16. And now you can put this value into the previous equation. For this equation, put the value of Z dash, what you will get is the value of E dash, which is around minus 77.5 electron volt. So, this is the second method by which you can calculate the energy of different orbitals of helium atom. Now, there is another method which is known as perturbation correction. So, what it does, it first calculates, assuming that there is no repulsion between electrons, and now repulsion between electrons is considered as your perturbation, and you can calculate the energy due to this perturbation by using this formula. So, if you solve this integral, what you are going to get is your what is known as first order perturbation. And here you see this is your potential energy, this is written in atomic. It means that what we have done is we have removed your the constant terms, and if you plug in here and then integrate this, what you are going to get is E n 1. What you are going to get is E n 1, which is the first order perturbation correction for the helium atom, and that is equal to 5/8 Z E h, where this E h is your Hartree energy for Hartree energy. Okay. So, your energy is E naught is equal to the E naught naught, which is obtained neglecting the repulsion part, plus this, which is your perturbation, and if you add this, you will get minus 74.8 electron volt. So, these are the three different methods in which you can calculate the energy of orbitals associated with helium atom. Now, once we saw that, what we are going to look at is multi-electron system. So, without going into detail of mathematics, what I am going to tell you is qualitative analysis now. An important effect of electron repulsion is to remove the degeneracy of 2s 2p orbitals, 3s 3p 3d, which are degenerated in hydrogen atom. So, if you look at hydrogen atom, your energy is dependent on n value. So, 2s 2p has same energy, whereas 3s 3p and 3d has same energy. But when you take multi-electron system, this degeneracy is going to be removed. So, 2s 2p is going to have different energy. Similarly, 3s 3p and 3d are going to have different energy. So, if you see here 1s, 2s, 3s, now here 2s and 2p have different energy, 3s and 3p have different energy, 3s, 3p and 3d has different energy. So, here your energy is not only dependent on n, but it is also dependent on L value, and that is the effect of electronic repulsion. So, for multi-electron system, we need to understand two different concepts. One is called configuration and another is state. Configuration describes the way in which the electrons are distributed among various orbitals. For example, if I take the case of carbon, 1s orbital has 2 electrons, 2s orbital has 2 electrons, whereas 2p orbital has 2 electrons. So, this is known as configuration, but state is different. a configuration may give rise to more than one state. For example, 1s2, 2s2, 2p2 can give you more than one state of carbon, and what generally we get is 3 electronic states of different energy. I have talked about in case of at one electron system, I talked about how to get the electronic state during my previous lecture. In this, I am going to talk about how to get the electronic state of multi electron system. So, first I will discuss about non-equivalent electrons, and we will look for what are the states for atoms which have non-equivalent electrons. So, what I mean by non-equivalent electron? Non-equivalent electrons are those that have different values of either n or l. For example, 3p1, 3d1. So, here one electron has L value of 1, whereas the another electron has L value of 2. So, they have a different value of L, and thus these two electrons are not equivalent. Now, take the case of 3p1, 4p1. Although L value of the two electrons are same, but n value is not same. For one electron n value is 3, and for another electron n value is 4. And so, these are known as non-equivalent electrons. And getting states of non-equivalent electrons is not that difficult. So, let us think about excited state of carbon or silicon. They have electronic configuration p1 d1. So, for carbon it is 2p1 3d1, and for silicon it is 3p1 d1. So, first we need to find out L, that is what we discussed in the last lecture. So, this is your electronic configuration of excited state of carbon. So, one electron is in p level, so L1 is equal to 1, and one electron is in d level, so L2 is 2. And so, L is going to be from L1 plus L2 to L1 minus L2, and 1 plus 2 3 to 1 minus 2 mod, if you take mod of this is equal to 1. So, 3 2 1. So, there are 3 value of L, capital L, which is possible, and magnitude of this L will be 12 half h cross, 6 half h cross, and 2 half h cross. This is for this one, this is for this one, and this is for this one. H cross L, L plus 1. So, 3 into 4. So, this is your H cross into root 12 when L is equal to 3. L is equal to 3. Similarly, you can calculate for other value of L. So, this is LL coupling. So, this is a small l and L coupling. Now, let us go and look at the states. Once we calculated the L value, now we can label the different states, and the way we discussed last time, L is equal to 0 corresponds to S, L is equal to 1 corresponds to P, L is equal to 2 corresponds to state D, L is equal to 3 corresponds to state F. And we showed you last time that we have for carbon and silicon L is equal to 3, L is equal to 2, L is equal to 1. So, we have F state, D state and P state. So, both carbon and silicon is going to have F state, D state and P state. Now, let us see SS coupling. So, again S will be from S1 plus S2 to S1 minus S2. If we take 2 electrons, so 2p1 3d1 system, right. So, let us see 2p1 3d1 system. So, S is going to be your half for one electron, half for another electron. So, coupling will give you two state, S is equal to 0, S is equal to 1. So, label for terms indicate the value of S by having 2S plus 1 as pre superscript to SPD. That is what we discussed last time also. 2S plus 1 is known as multiplicity. So, now see what will the 2S plus 1? 2S plus 1 will be equal to 1 if S is equal to 0, and it will be equal to 3 if S is equal to 1. And so, the excited configuration of carbon and give 1p, 3p, 1d, 3d, 1f, 3f, and these all are superscript. So, please do it. So, it will be like a superscript. Okay, sorry for this, but it will be pre superscript. It will be before F, but as a superscript. Now, we have calculated L, we have calculated S. Now, we will look at LS coupling, and this also I have discussed in the last class. So, J is going to have value between L plus S to L minus S with the mod sign. If L is greater than S, then J can take 2S plus 1 value, and if L is less than S, then J can take 2L plus 1 value. Now, let us think about LS coupling in 3D term. So, for 3D, S will be equal to 1 because this is equal to 2S plus 1, and so S is equal to 1 for 3D and L is equal to 2 for D. What does this mean? Is L is greater than S, L is greater than S, and so you are going to have. So, let us see here. If L is greater than S, then J can take 2S plus 1 value, right. So, 2S plus 1 is 2 into 1 plus 1 is equal to 3 value, and 3 value will be J 3 to 1, 3 to 1, and this value will come in the term as subscript, 3 to 1, 3 to 1. So, total number of states for carbon or silicon of configuration P1 D1 will be your 1 P1, 3 P1, 3 P0, 3 P1, 3 P2, 1 D2, 3 D1, 3 D2, 3 D3, 1 F3, 3 F2, 3 F3 and 3 F4. That is what all combination of states will exist for carbon or silicon configuration. This is the excited state. Remember, it is not the ground state, it is not P2 configuration, it is P1 D1, it is excited state of carbon or silicon. So, they are going to have these many energy levels. So, you can go and practice a bit on these configurations, and their terms are given here. So, one electron in S, another electron in other S orbital, then you will get 1s 3s, and that is written as 1 comma 3s. So, these are the different terms for different configurations. So, for S1 D1 you have 1 3D, S1 F1 1 3F. So, these things you can practice it. Now, it is not that difficult, just you need to understand the concept. Now, we will go to equivalent electrons. Equivalent electrons are a bit different, because we have to take care of Pauli exclusion principle and Hund's multiplicity rule. So, let us see the with one example what do we mean by equivalent electron. So, let us look at the ground state of carbon. Now, we are looking at ground state of carbon, not the excited state. So, in the ground state of carbon there are 2 electrons in level P or level 2p. These electrons have same value of n and same value of L. So, these electrons have same value of n and same value of L, and so they are equivalent electrons. So, n is equal to 2, L is equal to 1 for both electrons, and as per Pauli exclusion principle, 2 electrons have different value of either ml or ms. They are not going to have same value of everything. Also, it should be noted that indistinguishability of the electrons has been taken into account when deciding about the different states. For example, combination ML1 is equal to ML2 is equal to 1, MS1 is equal to minus half, MS2 is equal to half cannot be included in addition to ML1 is equal to 1 and MS1 is equal to half, MS2 is equal to minus half, which is obtained from the first electron exchange. So, what I mean is if there are 2 electrons and this is p orbitals. So, one is like this, another is like this, another cannot be like this, and this is first Pauli exclusion principle. Now, second is thing which you need to remember that it can be like this, but writing this as down, this as up, this is not going to help. Thus, violates your indistinguishability of 2 electrons. So, these two are not different. So, now we are going to write the different combination of quantum number for these 2 electrons, and then we are trying to find out the terms. Now, let us see here. The first is we started with 1 1. It means that suppose you have a p orbital, okay. This is 1 0 minus 1. So, 2 electron in this one, okay, 2 electron in this one. Only one combination is feasible, and that is 1 1 half minus half. You cannot have this combination, cannot have this combination, you cannot have, you cannot write like this down, this up, this I already discussed you, and that is why there is only one combination. Similarly, if you look at when I put 0 0, then there is only one combination, minus 1 1, then there is one combination. So, if ML1 and ML2 are equal, there is only one combination possible. Now, let us take, if I take the ML1 is equal to 1 and ML2 is equal to 0, ML2 is equal to 0. Now, there are 4 possibilities. What are the 4 possibilities? Both can be up, one is up, another is down, this is down, this is up, and both are down. These all 4 possibilities exist. So, we have written all the possibilities. Now, similarly, if I take 1 minus 1, then I have 4 possibilities, and if I take 0 minus 1, there is 4 possibilities. So, we have looked at every case. So, 1 1, then 1 0, 1 minus 1, you see 0 1 0, I did not take 0 1 because 0 1 is here, 1 0 and 0 1. So, this 4 already we have taken into account. So, we do not need 0 1, and similarly 0 minus 1 we do not need, because those two are similar. So, you have this combination of terms. Now, what we will do is, this is the different combination of ml and ms value possible for 2 electrons. Now, what we are going to do is calculate the L value and S value, L value and S value for each combination. If you do that, you will get L is equal to 2, S is equal to 0, L is equal to 1, S is equal to 1, 1 0 1 0. So, this you will get. Once you do that, now try to arrange this. So, first look at 2 0 is here. So, this is 2 0, then you see 1 0, 1 1 0 I took, then 0 0, 1 0 0 I took, minus 1 0, minus 1 0 is here and minus 2 0. So, 5 combination will give you 1 D term. This 5 combination is going to give you 1 D term. Now, go and look at this 1 1. So, where is 1 1? You have 1 1, then 0 1. So, this is 0 1, then minus 1 1, this is minus 1 1, 1 0, where is this is 1 0, 0 0. So, this is 0 0, minus 1 0, minus 1 0, 1 minus 1, 1 minus 1, and 0 minus 1, 0 minus 1, and minus 1 minus 1, this one. This corresponds to 3p level, and 0 0 corresponds to 1s. So, this is the way to get the terms for your equivalent electrons, transfer equivalent electrons. You have to write all the combination of ml and ms, L or S. Just you need to keep in mind that you cannot repeat it, or you cannot violate your Pauli exclusion rule, and you must take into account indistinguishability of the electrons. Once you do that, then it is easy to get the terms for different terms for equivalent electrons. So, now say this, we looked at P1 D1 and P2 configuration. P1 D1 corresponds to non-equivalent electron and P2 corresponds to equivalent p electrons. What is interesting to note that the terms which arise from two non-equivalent p electrons, as in case of 1s2, 2s2, 2p1, 3p1 or 3d1 for carbon atom. So, let us 3p1, okay, we saw 2p1, 3p1. Only 1s, 3p and 1d are allowed for two equivalent electrons. So, what happens to other 3? They are basically forbidden by Pauli exclusion principle. They are basically forbidden by Pauli exclusion principle. Now, rule for derivation of term symbol for non-equivalent electron, that a vacancy in a subcell behaves like an electron. So, this is a very important rule. What it does is, if suppose you have a p4 electron, then you can look at the terms arising from p2 electron and that simplify the complicated combination of 4 non-equivalent electrons, 4 equivalent electrons. Terms when you are writing terms for 4 equivalent electrons, it will lead to several different combinations, and so it is easy for you to go and write different combination for P2, and your term symbol is going to be same for P2 and P4. So, a vacancy and subcell in a subcell behaves like an electron. For example, ground configuration of carbon 1s2, 2s2, 2p2 and oxygen give rise to same terms. Add to the excited configuration of carbon 2p1d1 and neon 2p53d1. So, this is a important simplification when writing for different terms. So, P2 is your 1s 3p 1d, P3 is 4s 2p 2d. So, these are the different terms for different type of equivalent electrons, and you can practice one of them to see whether you understood or not. Now, we know what are the terms which comes due to your electron repulsion, but now we need to know which one is of lowest energy without calculating lowest energy, or which energy state is the ground state, which energy state is the ground state. So, of the terms arising from equivalent electrons, those with highest multiplicity lie lowest in the energy. So, this is the rule which you need to remember, that the term with highest multiplicity is going to be lowest in energy. For example, carbon oxygen, we saw that it will give rise to 3 different terms, one is 3p 1d. Among these 3p term is lowest in energy, because this has highest multiplicity, whereas other 2 terms has lower multiplicity than 3p. But sometime what will happen, that if there are 2 terms with the same multiplicity, so although they have higher multiplicity, but there are 2 terms. For example, in this case, if you take D2 configuration, you have 2 terms 3p and 3f, which has the same multiplicity. Although they are higher than other terms, but 2 of them are equal, or 2 of them have equal multiplicity. In that case, lowest is the one with the highest value of L. So, if you compare between 3p and 3f, the term with highest value of L is 3f, and so 3f is the lowest in energy. 3f is lowest in the energy. So, first criteria is look for multiplicity, and the second criteria is look for the value of L. And in both things, what we are looking for is the maximum value of multiplicity, maximum value of L. Okay, so till now we did not discuss about spin orbit coupling. We looked at the terms based on electron repulsion, Now comes the spin orbit coupling. We have discussed it in the hydrogen atom case. Now again we are going to discuss it for equivalent electrons. The splitting of a term by spin orbit interaction is proportional to J value, and J value we know what is J value. J comes from this is J is basically total angular momentum, which is sum of orbital angular momentum plus your spin angular momentum. So, Ej minus 1 is Aj. So, it is proportional to value of J. Here Ej is the energy corresponding to J, and a multiplate results. So, spin orbit coupling gives rise to splitting of the peak or multiplate results. If A is positive, then component with smallest value of J lies lowest in the energy. So, this is very important. So, if they split, some will be of higher energy, some will be of the lower energy. But if value of A is positive, then J, the term with the smallest J value, will be lowest in energy, and in that case multiplet is said to be normal. But if A is negative, then multiplet is inverted, and in that case the energy will be just opposite. Okay. So, there are two further rules for ground terms which tell us whether a multiplet arising from equivalent electrons is normal or inverted. Normal multiplets arise from equivalent electrons when partially filled orbital is less than half filled. Inverted multiplet arises from equivalent electrons when a partially filled orbital is more than half filled. Let us take this case of titanium. So, it has 3 D2, 4 S2. D2 corresponds to 1s, 3p, 1d, 3f, 1g, these are the terms, and 3f is lowest in the energy. You see these two have 3p and 3f, both have same multiplicity and they have highest multiplicity. So, they are going to be lowest in energy. In between two, F has highest value of L, and so it is going to be the ground state. And again 3F will give you, so 3F means S is equal to 1 and L is equal to 0, 1, 2, 3. Here S is equal to 3, L is equal to 3, L is equal to 3 and S is equal to 1. So, it is going to have value from 4 to J value from 4 to 2. So, 4, 3, 2 and the lowest value of J is 2, and so ground state is going to be 3F2 since D is less than half filled, D is less than half filled. Now, take this case carbon, oxygen, they give 3 different terms. This one has highest multiplicity, and so this is going to be ground state. Okay. 3p is going to be ground state for both carbon and oxygen. Now, for 3p your S is equal to 1 and L is equal to 1, S is equal to 1 and L is equal to 1. So, it is going to have J value 2, 1, 0. So, it is going to have J value 2, 1, 0. Now, look here, now here there is difference. For carbon, the 3p0 will be the ground state, because in the carbon molecule your p orbital is less than half filled, but for oxygen it is going to be different. For oxygen 3p2 is going to be the ground state, since the p orbital is more than half filled, and so carbon will give you normal multiplet, whereas oxygen will give you inverted multiplet. So, please keep that thing in mind. Now, we will discuss about spectra of alkali metal. All alkali metal has one valence electron is outer ns orbital, n is 2 for lithium, n is equal to 3 for sodium, n is equal to 4 for potassium, and so on. Considering only orbital changes involving this valence electron, the behavior of electron resembles that of hydrogen atom. What is the reason? Reason is that core of alkali metal has net positive charge, nucleus charge has plus Zd charge and filled orbitals has Z minus 1 charge. Please change this charge. Thereby, they show similar effect on the valence electron as the nucleus of hydrogen atom also has one electron in its outermost orbital. Spectra of alkali metal can be excited in a discharge lamp containing a sample of the appropriate metal. Now, emission spectrum of hydrogen atom shows only one series, Balmer series, in the visible region. We are talking in the visible region, it shows only one series. While in the visible region, alkali metals show at least 3 series. The selection rule is same what we discussed for hydrogen atom, that delta n is unrestricted and delta L is plus minus 1. Selection rules, these selection rules lead to sharp, principal, diffuse and fundamental series if the promoted electron is in s, p, d and f orbital respectively. So, if a promoted electron is in s, then it leads to sharp series. If the promoted electron is in p, then it leads to principal series. If the promoted electron is in d, then it leads to diffuse series, and if the promoted electron is in f, it is called your fundamental series. So, here is the example, this is the diagram for lithium atom. You can see that from 2p it can go to 3s, it can go to 2p to all the s here of 2s term, and 2p to all the d of 2d term. And when promoted electron is in s, for example this, so this is called sharp series. Now, here you see it is going from 2s to 2p, 3p, 4p, 5p, 6p, delta n is unrestricted, you must remember that, and so this is known as principal series. Now, look at here p to d, since it is going to d, and so this is known as a diffuse series. Now, from d to f, this is known as fundamental series. Now, 2s to 3d is not allowed, because delta L is plus 2, but delta L can be minus 1. So, 2p to 3s is allowed. So, this is your diagram for the spectrum of the lithium. Now, these are the 4 different series. This is the fundamental, this is your n dash versus lambda. If n dash increases, then you see lambda is, this side is increased, so this side is decreased. Okay. So, it is decreasing. So, this is like diffuse, this is like sharp, and this is like principal. So, these are the 4 series in the emission spectrum of lithium. So, lithium can have, you see, if you look at the lithium, what is the ground state? 1s2 2s1, and that state is 2s half. When the excited electron goes to the p state, then you have these 2 terms. It can go to d state, that will lead to 2 different terms, and if it goes to f state, it can give you 2 different terms. So, this is about one electron going from the ground state to excited state. Excited state can be s level, can be p level, and can be d and f, and these are the different terms for different kind of excited state. So, in the sodium atom, promotion of, so now we will talk about sodium atom. In the sodium atom, promotion of 3s valence electron to any np orbital with n greater than 2 results in pair of these 2 states. This is same like lithium. Similar kind of things can happen in case of the sodium. Labeling of these state with n gives you n 2p half and n 2p 3 by 2. So, suppose we are discussing about 3s to 4p, then we will write 4 here, 4 here. If it is 3s to 5p, then we can write 5, 2p half and 5, 2p 3 by 2. N level is helpful for the state when only one electron is promoted and the unpromoted electrons are either in filled orbital or in a s orbital. N level can be used for hydrogen atom, alkali metal, helium atoms or alkaline earth metals. In other atoms, it is usual to proceed the state symbols by configuration of the electrons in unfilled orbital. For example, 2p, 3p, 1s0 state of carbon. Splitting between 2p half and 2p 3 by 2 states of sodium is 17.2 centimeter inverse, and it reduces with increasing n. So, if you look at the splitting the difference between 4 2p half and 4 2p 3 by 2, it will decrease. So, it will be 5.6 centimeter inverse, 2.5 centimeter inverse, 1.3 centimeter inverse for n is equal to 4, 5, 6 respectively. The splitting decreases rapidly with L, as exemplified by the splitting of only 0.1 centimeter inverse for 3 2d 3 by 2 and 3 2d 5 by 2 states. So, here splitting is very small compared to splitting between 3 2p half and 3p 3 by 2 states. All these 2p 2d multiplets are normal, the states with lowest j lying lowest in the energy. So, here is the different series of sodium atom. So, what we are looking at the from S to P and P to D. So, this is for S to P. So, promoted electron is going to be in P, here P to D. So, promoted electron is going to be in D. Since it is going to be in P, so this one corresponds to principal series and this corresponds to your diffuse series. Selection rule is delta J is equal to 0 plus minus 1, except J is equal to 0 to J is equal to 0 is not allowed. And you can see here 2s half, we saw that 2s has only one term, whereas 2p has 3 terms due to spin orbit coupling. So, 2p half, 2p 3 by 2, and so from here to here there is a possibility because delta J is 1, and here to here is a possibility because delta J is equal to 0. So, these two transitions satisfy selection rule, okay, and so you will get a simple doublet. Now, look at from P to D. P is split into two different states and D splits into two different states. You see the difference between these two states is high compared to the difference between these states. So, difference between 2p 3 by 2 and 2p half is higher comparison to difference between 2d 5 by 2 and 2d 3 by 2. So, we are talking about difference in energy levels, energy of these two levels. So, now you see from here there is only one possibility of transition. So, you are going from half to 3 by 2. So, delta J is plus 1, but you cannot go from 2p half to 2d 5 by 2, since delta J will be plus 2, which is not allowed. But from here transition to both the D state is possible, because you are going from 3 by 2 to 3 by 2, which corresponds to delta G is equal to 0, and then you are going from 3 by 2 to 5 by 2, where delta J is plus 1. And so, there will be a kind of a small doublet. But here one thing you must notice is that since this difference is very small, so these two will be quite almost merged into each other, and that is why this is known as compound doublet. Sodium shows simple doublet in the principal series, and that is well known sodium D lines. Series in sodium appears in the yellow region of the spectrum with components at 589.592 and 588.995 nanometer. These two excited state involved in sodium D lines are the lowest energy excited state of the atom. Consequently, in a discharge in the vapor at a pressure that is sufficiently high for collisional deactivation of excited state to occur rapidly, a majority of atoms finds themselves in this state before emission of radiation takes place. Therefore, D lines are quite prominent in emission. which explains the predominant yellow color of sodium discharge lamps. Now, let us talk about diffuse series of sodium atom. All members of a diffuse series consist of compound doublet, as I have shown in the previous slide, but the splitting of 2d 3 by 2 and 2d 5 by 2 state may be too small for the closed pair of transition to be resolved. If you remember, then I showed you that these two are quite, so since these two energy levels are quite close to each other. So, this looks like a single peak, and so what you will see is a kind of compound doublet rather than triplet. So, it is for this reason that set of 3 transitions has become known as compound doublet rather than a triplet. Now, selection rule for a spectra of helium and alkaline earth metals. So, selection rule for a spectra of helium alkaline earth metals are delta L is plus minus 1 for promoted electron and delta S is equal to 0. And so, this is your what is known as Grotrian diagram for helium, and this is your, you can see that delta L is plus minus 1, delta N it can go anywhere, delta S should be 0, and so you have a different kind of spectra. Now, this is alkaline earth metal, again you see 3s1 and now 3p is, now you have 3p0, 3p1, 3p2, and for p to d. So, this is your, you can say this is principal and this is transition associated with the diffuse series, and you can see that all 3 transitions are possible because you are going from 0 plus minus 1. Here there is only one possibility, from this place there is 2 transition possible, and from this state there are 3 transition possible. So, once you know the selection rule, it is quite easy to know how many transitions are possible, and that can tell you about how does the spectra of different metals look like. So, thank you very much for listening. I have taken lot of material from this modern spectroscopy by Hollis, and mathematical equations has been taken from fundamentals of molecular spectroscopy by Banwell. So, I will like to stop here and see you in the next class. Thank you very much.